Okay, so let's get started. I'm going to be mostly covering 5.3 in this lecture video. But before we get started, on section 5.3, what I wanted to say was just this one aspect that we hadn't talked about. So this is the fact that an n by n matrix, so if we're thinking about the eigenvalues of an n by n matrix, it can have no more than n eigenvalues, right? So in order to see why this is, we can think about where the eigenvalues come from. And these are the roots of the characteristic polynomial. So eigenvalues are roots of the characteristic polynomial. Okay. And we know that the characteristic polynomial is a degree n polynomial, right? For an n by n matrix. So a degree n polynomial has at most n roots. Right. And so this is the reason why. And so if you allow, so this isn't something we'll really get into, but if you allow complex eigenvalues, then every n by n matrix has exactly n eigenvalues. But here, if we are, we're thinking of this, we would be counting multiplicity. So that's algebraic multiplicity. So if we had two roots, well, let's say one double root, we would count that twice, right? Okay, so we won't be considering complex eigenvalues, so we won't get exactly n eigenvalues every time, but we have up to n, right? Okay, so now let's get into section 5.3, where we are talking about diagonalization, which we mentioned at the end of class last time, right? So let's first define what we mean by diagonalizing. So we say that a matrix, and this should be an n by n matrix. So a square matrix A is diagonalizable if it can be written, well, let's put it more simply, if it's similar to a diagonal matrix. We'll call that matrix D, right? Oh, I always miss the A in here. Diagonal. There we go. And so remember what it means to be similar is there exists a matrix P such that A is equal to P times D times P inverse. And so clearly P has to be invertible, right? And what we'll learn today is that we'll learn how to figure out what these matrices P and D have to be, right? So we have the diagonalization theorem, which tells us when a matrix is diagonalizable This is the diagonalization theorem. Okay, and maybe let me just say, so we say that a matrix is diagonalizable if it can be written this way, and then the process of actually doing that is what we call diagonalizing the matrix, right? Okay, so this will tell us when a matrix is diagonalizable. So an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. Okay. And if this is the case, then if this is the case and let's say V1 up to Vn, these are Rn linearly independent eigenvectors, then how we form this guy, the P times D times P inverse, is first of all, P is going to be the matrix of those linearly independent eigenvectors, right? So we just put them into a matrix, and then D is the diagonal matrix that has the eigenvalues on the main diagonal, right? So I'm just putting, maybe I'll make this a little bigger. So this giant 0 is just indicating that everywhere else is 0, right? Okay, so an important thing is that the vector, so here, the vector vi, right? So the ith vector in that list of n in linearly independent eigenvectors has eigenvalue lambda I. So I'm saying that those indices on the eigenvectors should match up with the indices on the eigenvalues, right? So wherever you position your eigenvector in the matrix P, the corresponding column should have the eigenvalue corresponding to it in the matrix D, right? So we just make sure that those line up. Okay, and when we do that, that's our P and our D. In order to write A in this way, right, like that, we would just need to find P inverse, and then we have our diagonalization of the matrix A, right? Okay. Now, one of the interesting applications of this diagonalization is taking higher powers of matrices, which is discussed in the textbook. Unfortunately, we won't be able to talk about it due to time. There are pretty interesting applications where you would want to take maybe like a 10th power of a matrix, but you can't do that in a very computationally efficient way because we talked about how matrix multiplication is pretty complex as a computationally, like if we're thinking of it that way. And so if you're interested in that at all, you can take a look in the textbook in this section 5.3. But we're going to move on and not talk about that too much. So if we're looking at this, right, this tells us exactly how to write A as this P times D times P inverse. And notice that if we're given a matrix A, what we'll need to know is the eigenvectors of A, right? So in order to the diagonalization theorem, says what this, well, let me put it this way. It means that in order to diagonalize A, we need to find its eigenvalues and eigenvectors. Whoops. Diagonalize A, need to find eigenvectors and eigenvalues. Okay. All right, so that's the first step in the process. I guess, and the second step is to check that they're linearly independent. Right. If they're not linearly independent, or if we can't find eigenvectors and eigenvectors that are linearly independent, then we know that A is not diagonalizable by the diagonalization theorem, right? This guy right here. Okay, so let's just quickly talk about why this is the case, right? So why the diagonalization theorem works. So let's assume first that the matrix A has n linearly independent eigenvectors. Right? Then what we do is we form P as we discussed above, right? So we make a matrix with columns V1 up to Vn. And this is going to be invertible because we know that the columns are linearly independent. So that's by the invertible matrix theorem. Okay. Next, let's think about the matrix D. So we know that, let me just move down here. So if we know that our matrix A is going to be similar to D, then we saw before that similar matrices have the same eigenvalues. And we also saw that diagonal matrices have their eigenvalues along the main diagonal, right? So if A is similar to D, then they must have the same eigenvalues. So we get that D is the matrix that we discussed before. So eigenvalues along the main diagonal, zeros elsewhere, right? This is what D has to be. Okay. And then we get our A is P times D times P inverse, and we've diagonalized A, right? So I guess, so A is diagonalizable. And conversely, if we start with the fact that A is diagonalizable, then that means that there exists a matrix P such that A is equal to P times D times P inverse, right? And again, D must have that form because similar matrices have the same eigenvalues. right? Okay. And so what we can say, so just starting from this equation that we have, we can multiply this on the right by P, right? So I have this, and then we know that P inverse times P is going to give us the identity. So this will simplify to A times P equals P times D, right? This is equivalent. And then if P has columns U1 up to UN, right? There's some columns, some vectors. Then what this says is that A times P will give us this. And on the other side, P times D, we're just replacing P with this form. And then we know that the matrix D looks like so, right? Okay. Now, on the left-hand side, we're going to use the definition of matrix multiplication. So we have our matrix P where we've written out the columns. We know that in the definition of matrix multiplication, the result of this matrix, this multiplication, the first column will be the matrix A times the column U1, right? So this will be my first column, and then we keep going and form all of the columns like that, right? And this is our left-hand side now, right? So just the one matrix with these columns. And then on the right-hand side, when we multiply this diagonal matrix by the matrix P, right? What we'll get is just the constant lambda1 times the first column, right? Like that. And then lambda2 times the second column, all the way up to lambda n times the last column, right? So we've just done that matrix multiplication on both sides of the equality. And so what we know now is if these two matrices are to be equal, then each of the columns should be equal, right? So this says that, in fact, let me just move down here. Okay, so this says that A times U1 is equal to lambda1 times U1, right? And equating each of the columns, we get this entire list of equalities. Maybe I'll just to emphasize. We can do A times U2 equals lambda2 times U2, and so on. Okay. And so now if we're looking at these equations, right? So maybe we can just focus on the first equation in this list, right? What's going on here is this looks exactly like our definition of being an eigenvector, right? And so we could try to say right here that this means that UI, let's use, yeah, so just in general, for each I between 1 and n, UI is an eigenvector of A, right, the matrix A, with eigenvalue lambda I, right? The only issue with making this conclusion is that we need that this is not the zero vector, right? Because we require that an eigenvector is not the zero vector, right? So if this was just satisfied for all, let's just maybe focus on this one. So if U1 was equal to the zero vector, then this equation unfortunately does not mean that U1 is an eigenvector. However, if we know ahead of time that U1 is not zero, then we can say that it is, right? So the reason why we know that each of these u's, each of the vectors u, are not zero is because we know that P is invertible, right? So since we know P is invertible, we know its columns are linearly independent. And so what that means is that none of these can be the zero vector, because we know anytime we include the zero vector in a list of vectors, it makes the entire thing linearly dependent, right? So we know that none of these can be the zero vector. So ui does not equal the zero vector for each I from 1 to n. Squeeze that in there. And so we know that, so we know that the columns of P, those ui's, are eigenvectors, each of them. Okay. Also, we know that they're linearly independent. And there's n of them, right? Okay, which is what we were trying to show. So remember that the statement of the theorem says that a matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So what we've shown is that assuming that the matrix is diagonalizable, then we do have n linearly independent eigenvectors. So that was the statement of the theorem, sort of the implication going in this direction. So diagonalizable implies n linearly independent eigenvectors. Okay, and that finishes off the proof, right? Okay. So one thing to just emphasize here is if an n by n matrix has n distinct eigenvectors, then what that means is that we already know, oh, sorry, not eigenvectors, I meant eigenvalues. Right. Okay. So if an n by n matrix has n distinct eigenvalues, then we know that they're linearly, well, the associated eigenvectors are linearly independent. So this means that the eigenvectors will be linearly independent. And this is from the theorem that we talked about in class. So this is by the theorem we from last class. Okay. So that said, that exactly this, that when you have distinct eigenvalues, then when you take the collection of eigenvectors, you have a linearly independent set, right? And so what this means, sort of the takeaway, is that if A has n distinct eigenvalues, n distinct eigenvalues, then we already know that A is diagonalizable, right? So this is a nice quick check, right, that you can do. So if you find the, oh, that looks terrible. Let me fix this. So if you find the eigenvalues of A and you have no repeated roots, then you already know from this theorem that your matrix is diagonalizable, right? You don't need to further check that there's linear independence, right? You can go ahead and move forward with your diagonalization. The other thing that means is if A does have repeated roots, so if you have a matrix A with repeated roots of the characteristic polynomial, roots of its characteristic polynomial, then for each of those repeated roots, well, let's say in order to have n linearly independent eigenvectors, which is the same as being diagonalizable. In order to get this, we need that the algebraic multiplicity of the eigenvalue is equal to the geometric multiplicity for each eigenvalue. Right. Okay. And remember, we saw before that the geometric multiplicity is in general smaller, so less than or equal to the algebraic multiplicity. Okay. So remember, the algebraic multiplicity is the number of times that it appears as a root of the characteristic polynomial, right? And the geometric multiplicity of the eigenvalue is the dimension of the eigenspace, right? And so in general, it can be smaller. We saw an example of a double root where the eigenspace was only dimension 1, right? And so if we have that the algebraic multiplicity actually matches the geometric multiplicity, then we should be able to get the right number of independent, linearly independent eigenvectors. Right? Okay. So let's get into some examples where we actually diagonalize a matrix, right? So let's start off by diagonalizing a 2 by 2. We'll diagonalize. So we have this matrix A. Okay, and as I'm going through this, I'm gonna like list out the steps for this first example. And then in the next one, I won't necessarily list out all the steps. But we start by finding the eigenvalues. Okay, so remember that the process is to look at the determinant of A minus lambda I, and whatever we get out of this is our characteristic polynomial, right? So my matrix is this guy here. And then when I multiply the identity matrix by lambda, what that does is replaces my ones along the diagonal with lambdas. Right? So I get this, and then I'll just do the, oh, we need the determinant of this, right? So we'll just stick that in there. So we're after the determinant of 1 minus lambda, 2, and then we have 2, 1 minus lambda, right? Okay, so this is just a simple 2 by 2 determinant. And then what we would want to do at this point is multiply this out, and then we'll try to factor it. So this will give us 1 minus 2 lambda plus lambda squared minus 4. And then rewriting that, we get this, which will factor nicely into lambda minus 3 and lambda plus 1, right? And so our roots are 3 and -1, and those are our eigenvalues. Right? Okay. Now the next step is to find our n linearly independent eigenvalues, right? So, or sorry, eigenvectors. So we want to find n linearly independent eigenvectors. And so functionally what that means is find a basis for each eigenspace. Okay. And so since we know that we have these two distinct eigenvalues, we should get one vector in each basis, right? And those will form our columns of P, right? So I'm going to start with lambda equals -1, just go in consecutive order, right? So for lambda equals -1, what we get is a minus lambda I is going to be a plus I, right? And then remember our matrix A was this guy, plus I is going to give us this matrix of all 2s, right? Okay. And the eigenspace for this particular eigenvalue, remember, is the space of homogeneous solutions of this equation, right? So the general solution of a minus lambda I equals 0, right? The homogeneous, oh, sorry, we need an x in here. So this is this matrix times x equals 0 is going to be, oh, perhaps I should reduce this quickly. Okay, so starting with our matrix 2, 2, 2, 2, we can cancel the bottom row because it's a multiple of the top row. So just drop that, and we can also scale our row to be 1, 1, 0, 0. Right. Okay. So what we get out of this is that x1 equals minus x2, and x2 is a free variable. And so we can write down the parametric vector form, which is this guy here, and we can pull out x2, so we get -1, 1, right? Okay. So that is going to be one of our eigenvectors, right? So let's just give it a name. So v1 is an eigenvector for lambda equals -1. Okay, and then we can also do this process for the other eigenvalue we got, lambda 3, and we just go ahead and compute a minus 3i. That's going to be our matrix A, where along the diagonal entries we subtract 3, right? So this is, wait, did I do, maybe let me do this in 2 steps. So our matrix A was this guy, 1, 2, 2, 1. Good. And then we're going to subtract from that 3, 0, 0, 3. Okay, good. Now we've got -2, 2, 2, -2. Okay. And then we row reduce this, so we can cancel the bottom row again. So we get this, and then we can scale by -1/2. That'll give us 1, -1, 0, 0. Okay, and then writing down the solution of the homogeneous equation, we get, x1 equals x2, and again, x2 is free. So the solution has the form x2, x2, which is just a multiple of the vector 1, 1, right? Okay. And so my V2 is an eigenvector for the eigenvalue 3. Okay. So the next thing that we want to do, so step 3, is to form P using the eigenvectors you found in step 2. And also form D with the corresponding eigenvalues. So like I mentioned before, these should line up, right? So if I let P be V1, V2, which was -1, 1, and then 1, 1, right? Those two vectors that we found, then D has to be the diagonal matrix where we put -1 in the first column and 3 in the second column, right? Because this eigenvalue corresponds to this eigenvector, and then our other eigenvalue 3 corresponds to the second eigenvector in the matrix. Okay, good. And then the last step is to compute P inverse. Okay, and we have our matrix P right here. So let me just copy that down. And we'll just go ahead and use the definition involving the adjugate. So first of all, the determinant of P is -1 minus 1. So that's -2. And then P inverse, remember, is 1 over the determinant of P times, we'll just put it this way, the adjugate of P. So we're going to get 1 over -2, and then we form the adjugate. So it's simple for a 2 by 2, right? We swap the diagonal entries, and then we negate the off diagonal entries, right? So we get this matrix, which once we put in that -1/2 will give us -1/2, 1/2, 1/2, and 1/2. Right? Okay, so what we have now is A is equal to P times D times P inverse, where P is this matrix here, D is this diagonal matrix, and then P inverse we just computed like that. Okay, and we can double check that when we multiply these together, we actually get back to the matrix A, right? So let's do a quick check. So if we do, I'm just going to copy this. And maybe I'll start with multiplying these first two matrices together, right? And so what I'll get is just 1, and then 3, and then -1, and another 3. Oops. Right. And then we have our other matrix here. And we can finish this off. So I think it would be nicer to do this multiplication with, if we pull out the 1/2 from that matrix. So remember, one of the properties of matrix multiplication is that we can pull out scalars, and we can actually pull it all the way out to the front here, like that. And then I'll just have this matrix here. Okay. And when we go ahead and do this multiplication, that's going to be -1 plus 3. So that's a 2, 4, and then that's another 4 and a 2. Good. And then when we multiply by the scalar, we just divide all of those entries by 2, which gets us back to our matrix A. Okay. Good. So I guess one nice thing about this type of problem is that you can check your work at the end, make sure you got to the right place. Okay. And now I want to do one more example where we diagonalize a 3x3 matrix. And this can be a lot more work because, well, one of the sticking points is that you could end up with a characteristic polynomial that's difficult to factor. And so I'll show you that this is one of the nicer examples. So this is a problem where the characteristic polynomial that you get is not too bad. And I'll show you how to do this in a natural way. Okay, so like before, our first step is to find the eigenvalues of this matrix, right? And so what we're looking at, maybe I'll write that down. So first step is we're going to find the eigenvalues, which means we want to compute the determinant of A minus lambda I. Right. Okay. Now that's going to be, equals the determinant of this matrix where we just subtract lambda from each of the diagonal entries. Right. So those will be my diagonal entries, and then all of the other entries stay the same. Right. So I'll have this. Right, this is the determinant I'm after. And notice that in this last column, we have mostly zeros. So this is probably a good choice for us for our expansion, right? Our cofactor expansion. I'm gonna move this over just a little bit. Okay, there we go. So let's compute this determinant by expanding along that last column. And if we sort of map this out to figure out the sign, we know that we alternate signs as we step through the matrix. So this is plus, minus, plus, minus, plus. So the sign on my expansion is going to be positive, and then we have the determinant of the 2x2 minor. Right. Okay. So that's going to give us our 1 minus lambda, and then we have 4 minus lambda times -1 minus lambda minus -6, so that's plus 6. Okay. Okay. And then once you're at this point, notice that, well, this is a 3x3, so our characteristic polynomial is going to be a degree 3 polynomial. But notice that we already have this 1 minus lambda factored out. So what we want to do is keep this, don't multiply it in. So don't multiply this in. And instead, we're going to multiply this out and try to factor it. Maybe I'll change colors so it's clear. So this portion right here, we want to multiply this out and factor. And so this is a reason why this particular example is nicer, because what we end up having to factor is a quadratic, not a cubic. And remember, always you can use the quadratic formula if you get stuck on factoring, at least if all you're trying to factor is a quadratic, right? Okay, so I'm going to skip over the steps of multiplying this out and simplifying. So it's just some simple algebra. This is going to be lambda squared minus 3 lambda plus 2, right? And then this factors nicely into lambda plus 3 and lambda minus 1. Or wait, sorry, positive. So lambda minus 2 and lambda minus 1. There we go. Okay. And then I can notice in this 1 minus lambda, I can pull out a negative, which will give me a lambda minus 1 that I can combine with this other lambda minus 1 there. So what I'll end up with is a, repeated root, and then a regular root, right? So my eigenvalues are let's put lambda equals 2 first, and then lambda equals 1. This is my double root. So algebraic multiplicity 2, right? Okay. So let's go ahead and find eigenvalue or eigenvectors for these eigenvalues. So next we want to find eigenvectors. Really, we want to find bases for the eigenspaces. Right? Maybe let's start with the double root, right? So for lambda equals 1, what we're hoping is that the eigenspace has dimension 2, because if the eigenspace only has dimension 1, then we don't have linearly independent eigenvectors, right? And so we can't diagonalize. But let's see what happens here. So we want to solve the homogeneous equation for this matrix. So this is A minus lambda I. Let's copy down our A. That was this matrix here. And then if lambda is equal to 1, this is going to be just 1 times the identity matrix. It doesn't change it, right? So just subtracting this matrix from our A, we get 3, 2, 1, negative 3, negative 2, negative 1, and 0, 0, 0. Okay. Okay. And then we can row reduce this. I will also skip over those steps because we've done lots of practice row reducing. Well, I guess it's actually kind of straightforward. Just looking at this matrix, notice that the second and third row are constant multiples of the first. So we can just cancel both of those, right? And then we can also scale our first row by 1/3, and we'll end up with this as our first row. And then the other two are all zeros now. Okay. And so the homogeneous solution will be x1 equals x2, and we have 2 free variables, right? x2 and x3 are free, which is good, right? That means that our basis is going to have 2 vectors in it. So that means that we write down our parametric vector form for the solution. and we get x2, x2, x3. And splitting this, we get x2 times the vector 1, 1, 0 plus x3 times the vector 0, 0, 1, right? And those are our two eigenvectors. So right, V1 and V2. Okay, and then what we want to do is consider the other eigenvalue, right? And in the interest of time, I will maybe just leave this as an exercise. So what you would want to do is compute a minus 2i. Maybe we'll put it this way. For lambda equals 2, we would want to row reduce a minus 2i and write down the solution. For the homogeneous equation, right? And what you should get is your solution is going to look like x3 times 3, 2, 1, like that. Okay. So what that means is that, so we just skip some steps in here. Now we just form, maybe just to get everything in the same notation, right? So we're taking V3 to be that vector 3, 2, 1, and then P we form by having the columns V1, V2, V3, okay? And plugging those in, what we'll have is this matrix. Okay, that's a 0. Okay. And so the corresponding eigenvalues for the first two columns, the eigenvalue was 1. So in our diagonal matrix, the first two diagonal entries are going to be 1. And then the last column corresponded to the eigenvalue 3. So this is our diagonal matrix, right? And then also, we can find P inverse, which remember we compute by row reducing the matrix P augmented with the identity matrix. Okay. And this is really not too bad, but I think we've done examples of this before. So if you want to try this yourself, what you are trying to do is row reduce until you have the identity on the left-hand side. And on the right-hand side, what you should get is this matrix here. Okay. And so this, what we get is our matrix P that we found times our diagonal matrix times this P inverse. Oh goodness. Okay, let me see if I can scooch this over. There we go. Right. And that is a diagonalized. Right? Okay. Now the last thing that I wanted to say was that diagonalizability is not related to invertibility. right? So if you know that a matrix is diagonalizable, you don't know anything about whether it's invertible or not, and vice versa. So these are unrelated concepts. So if we sort of form a table, okay, so say we have diagonalizable, invertible, and then not, oh, sorry, I wanted to do it this way. Diagonalizable versus not diagonalizable, and then invertible and not invertible. Okay, so I'm going to make a little table like this and give examples that fall into each of these categories, right? So an example, we'll stick with 2 by 2 because they're a little bit easier to tell. And so an example of a 2 by 2 matrix that is both diagonalizable and invertible is just the identity, right? Which, clearly is invertible. I guess we could say the determinant does not equal 0, so it's invertible. And also it's already diagonal, so definitely diagonalizable, right? Also, we have this example. So this will be diagonalizable because, again, it is already diagonal, but here the determinant is equal to 0, so not invertible. Right? Okay. Now, for the other two, this is an example of a matrix that is invertible but not diagonalizable, right? So the determinant does not equal 0, so we know that it's invertible. We need to check that it's not diagonalizable. So it does require a little bit more work, which I will leave as an exercise for you. But notice that we have that it's triangular. So we know that the eigenvalues are along the main diagonal. And so we have a 1 and a 1. That means we have a repeated root in our polynomial. And so when you have a repeated root, it's possible that the eigenspace doesn't have sort of the full dimension, right? Okay, I need to hurry up before my computer dies. So the last thing is this example. This is an example of a matrix that is not invertible. We can see that the determinant equals 0. And we would need to check that it's not diagonalizable again. But notice here, the main diagonal, we have zeros, right? And it's also triangular. So you're going to have one eigenvalue that is 0. And you can check that you don't get that the algebraic multiplicity matches the geometric. So you don't get that your eigenspace has a dimension of 2. Okay, so I will leave that there. Maybe I'll just quickly remind you that if you're looking at a triangular matrix, you can read off the eigenvalues. Those will just be along the main diagonal. So remember that it's really easy to tell the eigenvalues for a matrix that is either diagonal already, or upper triangular, or lower triangular. Okay, so make sure you do the quiz, and if you have any questions, feel free to bring them on Wednesday. I can clear up anything from this lecture. Okay, thanks, bye.